Every single story you have ever imagined could be a real place. This is the promise of the infinite planet hypothesis. It is a simple but staggering idea. In a universe that might be infinite, every planet you can conceive of should exist somewhere. Not just Earth-like worlds, but realms of pure fantasy. Worlds with diamond crusts, oceans of molten metal, and skies lit by twin suns. By the end of this journey, you will have explored 20 specific worlds that could be waiting in the darkness, each more incredible than the last. We will see how a planet could be locked in a permanent global hurricane, and what kind of life might glow in the dark of a sunless void. This hypothesis bridges the gap between known science and the furthest reaches of imagination. What is the most astonishing world you believe could be out there? The foundation of this idea rests on a principle astronomers call the cosmological principle. It states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the matter in the cosmos is evenly distributed, no single spot is special. Isotropic means it looks the same in every direction. This principle is a cornerstone of modern cosmology, supported by the cosmic microwave background, the faint afterglow of the Big Bang that appears remarkably uniform in all directions. Now, if the universe is truly infinite in size and matter is evenly spread across that infinity, the implications become mind-bending. Infinity is not just a very big number. It is a concept that transcends our everyday intuition. In an infinite space with a finite number of ways to arrange fundamental particles, patterns must eventually repeat. Not just similar patterns, but identical ones. Given enough space, every possible configuration of matter that can exist will exist, not once, but an infinite number of times. This is the logical engine driving the infinite planet hypothesis. Mathematically, it guarantees both repetition and boundless variation. Somewhere, there is an exact copy of Earth with a copy of you reading this script. Farther out, there is a version where you made one different choice this morning, and farther still, worlds diverge completely into realms of pure imagination. This is where the hypothesis connects to profound ideas in theoretical physics and philosophy. Physicist David Deutsch, in his book The Fabric of Reality, argues for a similar structure within the quantum multiverse. In his view, every possible outcome of a quantum event actually occurs, branching reality into a vast multiverse of parallel worlds. While the quantum multiverse deals with the subatomic branching of possibilities, the infinite planet hypothesis applies the same brutal logic of combinatorics to planets and solar systems on a cosmic scale. It is a zoomed-out, astronomical cousin of the multiverse idea. This is not merely science fiction speculation. It is a serious, albeit speculative, extrapolation from our best models of the cosmos. We know the universe is immensely vast and uniform. We know the laws of physics and chemistry are the same everywhere. If the universe has no edge, then there is no reason to believe the arrangement of atoms on our pale blue dot is uniquely special. The stage is set, then, for a tour of possibility itself. We begin our journey close to home with a world that is almost familiar yet profoundly alien. It is a planet caught in an eternal embrace, forever showing the same face to its star. This tidal locking creates two extreme realms, a scorching permanent day and a frozen eternal night. But in the thin ribbon of twilight between them, where the sun forever sits on the horizon, conditions might be just right for life to find a precarious and breathtaking foothold. Our twilight world is just the beginning. The first truly alien landscape on our list is forged not from rock and iron, but from the very element of life and luxury. We are entering the domain of the diamond planet. This is not a metaphor. In certain solar systems, the primordial cloud of gas and dust that forms stars and planets can be extraordinarily rich in carbon and relatively poor in oxygen. Here, the chemistry of planet building takes a dramatic turn. Instead of silicon and oxygen combining to make familiar silicate rocks like granite and basalt, carbon atoms seize the opportunity. Under the immense pressures inside a forming planet, they crystallize into a lattice of staggering strength and beauty. The crust of such a world could be a global layer of diamond, miles thick, interspersed with sheets of graphite, the soft, slippery form of carbon found in pencil lead. We have already glimpsed such a possibility in our own galaxy. The exoplanet 55 Cancri E, orbiting a star 41 light-years away, is a super-Earth with a radius about twice that of our own world. Based on its density and the composition of its star, astronomers strongly suspect its interior is rich in carbon. It may very well possess a core not of molten iron but of solid diamond, a treasure beyond comprehension locked away beneath a searing surface. This real-world discovery gives weight to the hypothesis: if one diamond-rich world exists in an infinite universe, there must be worlds where the diamond isn't buried but forms the very ground you walk on. Picture the landscape of such a place. Imagine mountains that are not dull stone but colossal, faceted crystals catching the light of a distant sun, scattering rainbows across valleys of black graphite. Rivers might not carry water, but viscous flows of heavy hydrocarbons, a thick, tarry substance oozing across the crystalline plains. The atmosphere could be a dense soup of carbon compounds, a perpetual smog of soot and complex organic molecules, turning the sky a hazy orange or a deep, murky brown. Storms on this world wouldn't be of rain, but of abrasive graphite dust sandblasting the diamond peaks over eons. The geology would be utterly alien. Tectonic plates of diamond grinding against each other might create mountain ranges of unbelievable sharpness and brilliance. Volcanic activity, if it exists, wouldn't spew molten rock, but perhaps superheated slurries of carbon and other exotic compounds. The very concept of erosion changes when the bedrock is the hardest naturally occurring substance known. A single, planet-wide diamond crust presents a vision of both breathtaking beauty and profound strangeness, a world where the ground itself is a jewel, and the rules of our familiar geology are rewritten into something spectacular and new. But a diamond crust is a static, geological marvel. The next world on our list is a dynamic, living paradox, a planet caught in a permanent state of dramatic tension. This is the eyeball world, a planet tidally locked to its star, forever presenting the same face to the light. The name comes from its appearance from space, a staring eye gazing into the cosmos. One side is a blazing, sun-scorched desert in perpetual, searing daylight. The opposite hemisphere is a frozen wasteland plunged into eternal, airless night. But between these two extremes lies a narrow, miraculous ring, the Terminator line. Here, the sun forever hangs on the horizon, casting the land into an endless, rosy twilight. This is the planet's iris, a thin band where conditions might be just right for liquid water and perhaps for life. The physics of this are both simple and severe. With one side constantly heated and the other constantly radiating heat into space, a titanic temperature difference builds. This doesn't create a gentle breeze, it fuels planet-wide hurricane-force winds, screaming from the hot side to the cold side in a desperate attempt to balance the energy. These winds would funnel along the Terminator line, a roaring river of atmosphere trapped between a furnace and a freezer. On the star-facing side, oceans would boil away into a thick, steam-filled sky. On the night side, the atmosphere itself might freeze out, falling as snows of nitrogen or oxygen, creating glaciers of air. But in that twilight band, something miraculous could happen. Glacial ice from the dark side could creep forward, meeting and melting against the warmth bleeding from the day side, creating a slushy, liquid ocean that encircles the entire world. Imagine standing on a shoreline in this perpetual dusk. To one side, a boiling sea vanishes into a haze of steam and blinding light. To the other, a wall of blue ice climbs into an abyss of stars. The sky above you is a permanent sunset, while underfoot, the very ground is a battleground between fire and ice. This is not pure fantasy. Astronomers have identified real candidates for such worlds. The closest exoplanet to us, Proxima Centauri b, orbits a red dwarf star in its habitable zone. It is almost certainly tidally locked. While we don't yet know if it has an ocean or an atmosphere, the conditions for an eyeball planet are there. If it possesses water, its most likely haven is that thin, circular strip of twilight. Life here would face extraordinary constraints. It couldn't spread across the globe, only along this linear oasis. Plants, if they existed, would not track the sun across the sky. They would all lean perpetually toward the horizon. Animals might migrate not north and south, but in a never-ending circle around their world, following the narrow band of tolerable temperatures. The entire ecology would be one-dimensional, a ribbon of biology wrapped around a sphere of extremes. The eyeball planet shows us that habitability doesn't require a globally temperate climate like Earth. It can be a precarious, razor-thin balance, a fleeting compromise between two hellish realms, proving that life, if it exists, will find a way in the most unforgiving and geometrically strange of places. The delicate balance of an eyeball world is a study in extremes, but our next destination is a monument to cosmic violence. This is the Chthonian planet, a world born from catastrophe. Its name comes from the Greek chthonic, meaning of the underworld, and it is a fitting title for a place that is essentially the ghost of a gas giant. Imagine a planet like Jupiter or Saturn, a colossal sphere of hydrogen and helium with a relatively small rocky or metallic core. Now picture that giant world drifting inward, pulled by the relentless gravity of its star until it orbits dangerously close, skimming the stellar furnace. Here, the star's intense heat and radiation act like a cosmic blowtorch. Over millions of years, the immense atmosphere of the gas giant is boiled and blasted away, stripped molecule by molecule into the void of space. What remains is not the familiar banded sphere, but the exposed, naked core of the former giant. This is the Chthonian planet, a colossal ball of metal and rock, once buried under thousands of miles of gas, now laid bare under an angry sun. The surface of such a world is a vision of hell itself. With its star so close, the planet is likely tidally locked, one hemisphere perpetually facing the inferno. Temperatures on that dayside could soar to thousands of degrees, hot enough to melt iron, nickel, and even platinum. The landscape might be a global ocean of molten metal, shimmering with vicious heat, with continents of slightly higher melting point alloys breaking the surface like slag in a furnace. The sky, what little atmosphere might remain, would be a thin haze of vaporized metals glowing with a sickly, metallic light. Radiation from the nearby star would bathe the surface in a deadly, constant barrage, sterilizing any possibility of life as we know it. It is a place of pure, elemental fury, yet within this apocalyptic scenery lies a treasure beyond imagining. That exposed core would be phenomenally dense, a concentrated lump of heavy elements. After the lightweight hydrogen and helium are gone, what's left are the rare and valuable materials iron, nickel, gold, platinum, uranium, and other exotic metals forged in ancient stellar explosions. A single Chthonian planet could contain more accessible heavy metals than an entire solar system's worth of conventional rocky worlds. This makes it the ultimate prize for a far future, unimaginably advanced mining civilization. The logistical challenges are staggering, requiring technology to withstand temperatures that vaporize spacecraft and radiation that fries electronics. But the potential reward, a nearly pure metal world, might justify the inconceivable effort. Such an operation would not look like a mine on Earth, but more like a stellar-scale refining facility, perhaps using magnetic fields to siphon molten metal directly from the planetary ocean. The profound mystery, however, lies beneath that searing surface. What is the interior structure of a Chthonian world? Without the crushing weight of a giant planet's atmosphere, would the core decompress and change? Could there be strange, ultra-dense crystalline structures of metal that form under such intense heat and pressure, materials that don't exist anywhere else in the universe? Or perhaps in the eternal night of the planet's far side, where temperatures might plummet, some remnant of the ancient atmosphere froze into exotic ices, creating a stark dichotomy between a hemisphere of fire and one of frozen, heavy gases. The Chthonian planet is a stark reminder of the dynamic brutality of solar systems. Worlds are not permanent. They can be transformed, unmade, and reborn into something entirely new and terrifying by the simple, relentless mechanics of gravity and stellar wind. It is a tombstone for a gas giant and a vault of cosmic treasure all in one. A Chthonian world is a monument to a star's destructive power, but some planets escape that fiery fate entirely by being cast out into the coldest dark. This is the rogue planet, a world without a sun. Imagine the profound silence of a solar system, the gentle gravitational dance of planets around their star. Now picture a violent gravitational encounter, perhaps a close pass with a gas giant that flings a smaller, rocky world like a stone from a sling. It breaks free from its star's embrace entirely, its orbital path becoming a straight line into the endless night between the stars. This is not a rare theoretical fluke. Simulations suggest our galaxy alone may be filled with billions, even trillions of these nomads, far outnumbering the stars themselves. They are the ghosts of solar systems past, drifting unseen through the interstellar void. The environment on such a world is beyond our earthly comprehension of day and night. There is no sunrise, no sunset, only an eternal, star-studded blackness. The sky is not blue, but an absolute velvet black, punctuated by the cold, unwavering pinpricks of distant suns that provide no warmth, only a faint, ghostly light. Without a nearby star, the surface temperature plummets to just a few degrees above absolute zero. The atmosphere, if it wasn't stripped away during the ejection, would freeze solid, falling as snows of nitrogen, oxygen, and carbon dioxide, creating a global glacier of air over a frozen rock. The surface is a perpetual, airless ice ball, a crypt of frozen geology. It seems like the most sterile, dead place imaginable, yet deep within this frozen tomb, life might find a way. The source of heat is not a sun, but the planet's own inner fire. Radioactive elements like uranium and thorium in the core decay, providing a slow, steady trickle of geothermal warmth. Or if the planet has a large moon that was ejected with it, their gravitational tug of war could create tidal forces, flexing the interior and generating heat through friction, just as Jupiter's gravity heats the interior of its moon Europa. This internal warmth could be enough to maintain a vast global ocean of liquid water, trapped between a frozen, rocky core and a crust of ice dozens of miles thick. This creates a breathtaking scenario, a lightless subsurface sea adrift in the interstellar darkness. In our own solar system, Europa and Enceladus have such oceans, warmed by tidal forces from their giant planets, and they are prime candidates in the search for alien life. A rogue planet's ocean would be similar but utterly isolated. It would be a world with no connection to the surface, no seasons, and no concept of a sky. Any life here would evolve in perpetual darkness, likely around hydrothermal vents on the ocean floor, drawing chemical energy from the planet's interior. It could be a biosphere of blind, pale creatures, or perhaps organisms that generate their own faint, bioluminescent light, creating their own constellations in the abyssal black. The entire ecosystem would be sealed in a watery snow globe, wandering the galaxy, completely unaware of the universe outside its icy shell. Detecting such a world is one of astronomy's greatest challenges. It emits almost no light of its own and reflects none. We might only spot one if it passed directly in front of a distant star, causing a fleeting, one-time microlensing event where its gravity briefly bends and magnifies the star's light. Even then, we would get only a single data point before it vanished back into the dark. Reaching one is a logistical nightmare, requiring a spacecraft to navigate the trackless void between stars with no solar power, aiming for a target that gives off no signal to home in on. The rogue planet represents the ultimate hidden oasis, a secret garden of potential biology sailing silently through the cosmic ocean, a reminder that a world does not need a sun to be a cradle, only a heart that is still warm. A rogue planet drifts in eternal night, but our next destination is bathed in the light of not one but two suns. This is the binary sunset world, a scene straight from science fiction made scientifically plausible. The iconic double suns of Tatooine are not just a filmmaker's dream, they are a common feature of our galaxy. Astronomers estimate that around half of all star systems contain two or more stars orbiting each other. Where there are stable orbits, there can be planets. The key word, however, is stable. A planet in a multi-star system faces a gravitational ballet of immense complexity. It might orbit far outside both stars, treating them as a single, twinned light source at the center of its solar system. Alternatively, it could orbit just one of the stars in a tight, stable circle, while its parent star itself dances with a distant companion. Each configuration paints a different sky and creates a different world. The celestial mechanics lead to seasons and days of beautiful chaos. Imagine a year where the distance to each star changes dramatically as they orbit each other, leading to superheated summers when the planet is near both suns, and deep, complex winters when one star dominates. The day-night cycle becomes a mesmerizing puzzle. Some days, both suns rise and set together, casting overlapping, faint double shadows. Other times, one sun might linger on the horizon for hours after its partner has set, bathing the landscape in an extended, eerie twilight. There could be periods of perpetual daylight if the planet's orbit and rotation align so that one sun is always in the sky, or brief, profound darkness when both dip below the horizon together. The vistas are beyond anything on Earth. Picture a sunset where a large orange star sinks below the mountains, while its smaller, white companion still hangs high in a purple sky, its cooler light casting long, blue-tinted shadows. Plants on such a world would face a unique challenge, adapting to light that changes not just in intensity, but in color and spectrum throughout the year and even throughout the day. Flora might develop leaves that can adjust their photosynthetic chemistry on the fly, or different layers of vegetation could specialize in absorbing light from one star or the other. The climate would be a turbulent masterpiece driven by competing gravitational tides and shifting heat sources, potentially creating global wind patterns that reverse with the stellar seasons. This world is a testament to cosmic harmony emerging from complexity, a place where the sky itself is a dynamic, ever-changing work of art, proving that even the most iconic fantasy landscapes have a firm footing in the dazzling mathematics of reality. Binary sunsets paint a sky of complex beauty, but our next world has no sky at all, at least not one you could ever see. This is the water world, a planet swallowed whole by a single global ocean. Forget continents, forget islands, forget even a shoreline. From pole to pole, the surface is an unbroken expanse of deep, rolling water, stretching hundreds of miles down to a seabed of solid, super-compressed ice. Such a world begins not with rock, but with a staggering delivery of water, perhaps from countless icy comets bombarding a young planet, or from a primordial nebula extraordinarily rich in hydrogen and oxygen. The result is a thalassigen, a waterborne world where the very concept of geology is turned upside down. The pressures in the depths of this endless ocean are almost beyond comprehension. As you descend, the weight of the water above you builds exponentially. Long before you could ever reach a theoretical seafloor, something extraordinary happens to the water itself. Under pressures hundreds of thousands of times greater than Earth's atmosphere, the familiar molecular structure of liquid water collapses and rearranges. It crystallizes into exotic forms of ice, not because it's cold, but because the pressure is so immense. This is Ice 7, a cubic crystalline form of water that remains solid at temperatures far above boiling. In the abyssal trenches of a water world, you would find not a dark, muddy bottom, but a glowing, hot floor of solid ice, a surreal landscape where the very ocean turns to a solid ceiling above a deeper, denser layer. Life in such an environment would face unique challenges and opportunities. With no land to provide minerals, the nutrient cycle would be entirely vertical, dependent on upwelling from the deep or delivered by rare asteroid impacts. The surface could be covered in vast, planet-wide algal mats, floating cities of simple organisms harvesting the sunlight, their collective metabolism possibly altering the entire world's atmosphere. Deeper down in the eternal twilight zone, intelligent species might evolve. Without the need to build shelters from wind or weather, their civilizations could be based in vast, drifting kelp forests or around geothermal vents on the hot ice boundary. Communication might rely on complex patterns of bioluminescence or low-frequency sound that travels for thousands of miles in the dense water. And in the deepest, most pressurized realms, true leviathans could exist, creatures with biology built around fluid-filled bodies to withstand the crushing force, perhaps grazing on the strange chemical soups that seep from the planet's hot, icy crust. The most profound mystery of a water world lies at its very heart. With so much mass in its ocean, the traditional layers of a rocky planet are inverted. The crust is not stone, but that thick, global shell of high-pressure ice. Beneath it, there might be a mantle of even more exotic, superionic water, a state where oxygen atoms form a lattice while hydrogen ions flow through it like a liquid metal. And at the very center, a small, dense core of silicate rock and metal, the only remnant of the original, dusty world that first gathered this unimaginable cloak of water. This core, heated by radioactive decay and insulated by hundreds of miles of ocean and ice, could be the planet's only source of new rock, with volcanic activity possibly creating temporary, fleeting islands of pumice that float for a time before being dissolved or dragged back down into the abyss. A water world is a planet of pure, relentless fluidity, a reminder that the most common compound in the universe can, in sufficient quantity, become the very architecture of a world, crafting an entire biosphere in its dark, pressurized, and utterly alien depths. The crushing pressure of a water world is a force of containment, but on our next destination, the atmosphere itself becomes a crushing ocean. This is the super-Earth with a super-dense atmosphere, a world where the sky weighs more than the sea. Picture a planet several times more massive than our own, its powerful gravity acting like a cosmic vise, clinging to an atmosphere of carbon dioxide and other gases hundreds of times thicker than Earth's. The result is a runaway greenhouse effect of staggering proportions. The surface temperature soars to hundreds of degrees, hot enough to melt lead and zinc into shimmering metallic puddles. Yet, paradoxically, high above this furnace, in the upper reaches of the bloated atmosphere, conditions might be surprisingly mild. At an altitude where the pressure equals Earth's surface, the temperature could be a balmy, shirt-sleeve environment. This creates a world with two utterly alien surfaces, one of scorched rock below and a potential haven of clouds above. Descending through that orange, soupy sky would be a journey into a perpetual red-lit twilight. So much atmosphere hangs overhead that the sun, even at noon, would be just a faint, diffused patch of brighter glow in a featureless, oppressive orange ceiling. The light that reaches the ground is a dim, hellish red, like the embers of a dying fire. The geology here is sculpted by heat and phenomenal pressure. Mountains would be squashed, their peaks broad and flattened. Valleys might be filled with lakes of molten metal or sluggish rivers of molten sulfur. And there is a possibility of something truly surreal, floatstones. On Earth, pumice is a volcanic rock so full of air bubbles it can float on water. On this high-pressure world, certain rocks formed under peculiar conditions could be less dense than the incredibly thick, supercritical air. Imagine boulders of porous, lightweight stone not resting on the ground, but drifting slowly in the dense atmosphere, like submarines in a slow-motion sea, casting long, distorted shadows across the molten landscape below. Exploring such a world presents challenges that make other planets seem hospitable. A lander would need to be built like a deep-sea submarine, engineered to withstand not just extreme heat, but pressures that would instantly crumple any craft designed for Mars or Venus. Communication through hundreds of miles of dense, ionized atmosphere would be nearly impossible, and any notion of stepping outside is pure fantasy. The combination of heat, pressure, and toxic chemistry would obliterate a human in an instant. Our only window to this environment might be through resilient robotic probes, sinking for days through the murky orange haze, sending back fragmented data of a world where the very air is a crushing, hot, and heavy ocean. This super-Earth is a lesson in atmospheric extremes, showing us that an atmosphere is not always a gentle blanket. It can be a smothering, heavyweight cloak, transforming a rocky world into a pressure cooker of surreal and forbidding landscapes. A super-dense atmosphere smothers a world in pressure, but there exists an environment where the very fabric of space and time is twisted by a dead star. Orbiting a pulsar is to live in the aftermath of a stellar cataclysm. A pulsar is the rapidly spinning, hyper-dense corpse of a massive star that died in a supernova explosion. It is a city-sized sphere of pure neutronium, a material so dense a single teaspoon would weigh billions of tons on Earth. As it spins, sometimes hundreds of times per second, it beams out focused lances of radiation, X-rays and gamma rays, like a cosmic lighthouse of pure death. Any planet caught in that sweeping beam is sterilized over and over again by an energy barrage that would strip away atmospheres and tear apart molecules. The very idea of a planet surviving here seems impossible, yet astonishingly we have found them. The first exoplanets ever discovered, back in 1992, orbit a pulsar named PSRB 1257+12. They are a testament to cosmic resilience, worlds born from absolute destruction. They likely did not form with their star. Instead, they are probably second-generation worlds, assembled from the heavy element debris of the supernova that created the pulsar itself. Imagine the crust of such a place, forged not in the gentle accretion of a protoplanetary disk, but in the unimaginable heat and pressure of a stellar explosion. It could be a layer of exotic, radioactive minerals, elements like uranium and plutonium woven directly into the bedrock, making the ground itself faintly glow with an eerie, persistent light. The surface would be a barren, airless plain, constantly scoured by the pulsar's relentless wind of high-energy particles. But the true strangeness of a pulsar planet is not just its origin or its irradiated surface. It is a distortion in time itself. A pulsar's gravity is so intense that it significantly warps spacetime around it. According to Einstein's theory of general relativity, time passes more slowly in a strong gravitational field. For an observer on this world, time would crawl compared to the rest of the universe. A single hour on the surface might equate to years passing elsewhere. This means any robotic probe we sent would, from our perspective, seem to move in agonizing slow motion, its signals stretched and red shifted into near oblivion. To stand on such a world would be to watch the universe outside speed up in a silent, terrifying fast forward, stars streaking across a black sky, while you are trapped in a bubble of stretched out moments under the dead eye of a spinning tombstone. It is the ultimate expression of a hostile environment where the dangers are not just chemical or thermal, but fundamental, woven into the physics of reality itself. The pulsar's domain is one of absolute finality, but our journey now turns from the graves of stars to the nurseries of worlds, from solitary planets to a celestial partnership of fire and ice. We arrive at a tidally heated moon, a world whose very heart is set ablaze not by a sun, but by the relentless gravitational embrace of its parent planet. Picture a moon the size of our own, but orbiting a gas giant like Jupiter. If that giant world resides in its star's habitable zone, the stage is set for a profound duality. The moon receives gentle stellar warmth from afar, but its true engine lies within, stoked by an invisible force. As it orbits, the gas giant's immense gravity pulls on the moon, stretching and squeezing its interior like a ball of clay in a giant's hand. This constant, rhythmic flexing generates immense friction, and that friction turns to heat. The result is a world of spectacular, continuous volcanic fury. This is the fate of Jupiter's moon Io, the most volcanically active body in our solar system, but here we imagine it translated to a larger stage with even higher stakes. The surface of such a moon would be a constantly shifting hellscape. Volcanoes erupt not as rare events but as permanent features, spewing fountains of molten rock and sulfur hundreds of miles into a thin, toxic sky. Rivers of lava carve fresh channels across the crust daily, while lakes of molten silicate simmer in vast calderas. The landscape is newborn every hour, a world without erosion, without ancient mountains, just a perpetual churning rebirth of geology. The entire crust might be a global puzzle of volcanic plains, cracked and rewelded by the unending heat below. Yet, for all this surface violence, another possibility exists just beneath. If the moon has a significant amount of water, that same tidal heating could maintain a global ocean. But here, the heat's effect creates a stunning contrast. Instead of melting the surface, it might be just enough to keep a thick shell of ice liquid underneath. Imagine a moon with a surface of solid ice, smooth and white, stretching to the horizon. But this icy crust is not a dead lid. The tidal forces flexing the interior would crack it open, creating fissures and fractures. From these wounds, colossal geysers erupt, shooting plumes of salty water and organic molecules into space, a sight we witness on Saturn's moon Enceladus. This creates a world of two faces, a cold, icy exterior hiding a warm, dark, watery heart. The potential for life in such a place is immense. On the volcanic version, the energy for chemistry is everywhere, in the heat of the vents and the rich mineral soups of the lava flows. Around deep-sea hydrothermal vents in such a subsurface ocean, protected from the chaos above, the building blocks of life could assemble in a stable, energy-rich environment. This moon offers not one, but two potential crucibles, a surface forge of fire and rock, and a hidden, abyssal garden of water and chemistry. It is a world where the line between hell and haven is paper-thin, dictated by the simple, relentless rhythm of an orbital dance. The volcanic fury of a tidally heated moon is a spectacle of raw geology, but the foundation of any world, its very substance, is decided long before by a simple cosmic ratio. Across the galaxy, two elemental titans compete to build planets carbon and oxygen. Their relative abundance in the swirling cloud that forms a star and its planets dictates an entire world's destiny, creating a fundamental split between two cosmic families, the silica worlds and the carbonia worlds. Our Earth is the quintessential silica world. Our solar system's protoplanetary disk was rich in oxygen. When the cosmic dust settled, oxygen atoms readily bonded with silicon, the universe's favorite rock-forming element. This marriage created silicates, the minerals that make up 95% of Earth's crust, from the granite of mountains to the quartz in beach sand. Silicon and oxygen form strong, stable bonds, creating a diverse and robust geological palette. Water, hydrogen bonded with oxygen, became our life-giving solvent, carving valleys and filling oceans under a sky scattered by nitrogen and oxygen molecules. This is the familiar, rocky, watery blueprint we know, but in a different stellar nursery, one enriched by the remnants of ancient carbon-rich stars, the chemistry flips. Here, carbon atoms outnumber oxygen. In this environment, oxygen is quickly captured by more eager elements, leaving carbon free to dominate. Carbon, the versatile architect of organic molecules, now becomes the primary builder of planets. Instead of silicon-oxygen rocks, you get carbon-carbon and carbon-metal bonds. The crust solidifies not into granite, but into compounds like silicon carbide, a dark, ultra-hard ceramic, or, under sufficient pressure, into vast sheets of graphite and diamond. The sand on such a beach wouldn't be tiny quartz crystals, but grains of carbon, soot, or even microscopic diamonds. The very ground is fundamentally different. This elemental shift changes everything, right down to the potential for life. On a silica world, water is the obvious solvent, its polarity perfect for dissolving salts and facilitating the complex chemistry of biology as we know it. On a carbonia world, water might be rare or frozen solid, but another molecule, abundant in such a carbon-rich environment, could take its place, liquid methane or ethane. These hydrocarbons, flowing in rivers and pooling in vast, cold seas, could serve as an alternative solvent for a biochemistry built not on oxygen and water, but on carbon chains and long, complex hydrocarbons. Imagine a life form whose blood is a liquid hydrocarbon, whose cells are structured with benzene rings instead of phospholipid bilayers, thriving in temperatures hundreds of degrees below zero where water is a rock. The sky above this world would tell its own chemical story. Instead of our familiar blue scattering from nitrogen and oxygen, a carbonia atmosphere, thick with organic haze and hydrocarbons like methane, might cast a permanent, smoggy orange or a deep, melancholic brown over a landscape of dark, crystalline plains. From the ground you walk onto the liquid in its seas and the color of its sunset. A planet's identity is written in the simple, ancient ledger of carbon versus oxygen, proving that the universe builds with more than one set of blueprints. The chemistry of a world defines its substance, but the architecture of its sky can define its very soul. Our next world is adorned with a crown of such impossible scale it reshapes the planet beneath it. This is a world with a ring system 1,000 times more massive than Saturn's. We are not talking about delicate bands of ice, but a colossal, dense disk of rock and dust, wide enough to cast a permanent, moving shadow across entire continents. From the surface, this isn't a feature in the sky, it is the sky, a solid-looking arch of polished stone and glittering ice that bisects the heavens from one horizon to the other. The orbital mechanics create a life defined by light and shadow. The rings orbit in the planet's equatorial plane, and because they are so vast and dense, they block a significant portion of sunlight for the latitudes directly beneath them. This creates not a simple day and night, but a tripartite rhythm. There is full daylight in the polar regions, a deep, star-flecked night on the far side of the planet, and beneath the rings themselves, a perpetual, dappled twilight. The shadow of the ring isn't static, it sweeps across the landscape like the hand of a cosmic clock, creating bands of unique ecosystems that migrate with the passing hours. In the penumbra, the dim light would favor flora with huge, dark leaves to capture every photon, and fauna with enormous, sensitive eyes. These twilight forests might glow with constant, muted bioluminescence, a soft rebellion against the endless half-light. Human or alien civilization here would be built in the shadow of the arch. The ring would dominate mythology, science, and daily life. It might be worshipped as a god, the Great Arch, a divine bridge between realms or a celestial barrier holding back chaos. Calendars and timekeeping would be based on the ring's position and the passage of its shadow across known landmarks. Navigation would not rely on stars or a sun, but on reading the intricate patterns of light and dark within the ring itself, using specific bands or gaps as fixed points in the sky. The concept of a naked, starry night might be unknown to entire cultures living under the ring's permanent embrace. And then there are the celestial spectacles. Twice a day at the horizon, the planet's rotation would bring the ring into view or hide it, creating a ring rise and ring set. Picture the sun rising, but before its light crests the hills, a band of the ring begins to glow at the edge of the world, a curve of molten gold and copper that expands into the full, breathtaking arch. At night, the ring might catch the light of the planet's moons, casting a faint, pearly glow, a second, cooler sun that never sets. Meteor impacts on the ring could create temporary, brilliant flares visible from the ground, interpreted as omens or messages from the sky. This world is a testament to how a single, grand astronomical feature can write the story of a planet, dictating its ecology, inspiring its cultures, and offering a daily sky show of humbling, unparalleled beauty. The majesty of a ringed world gives way to a sky of pure, screaming chaos. This is the planet of the perpetual storm, a world where the weather map shows only one feature, a hurricane that never ends, wrapping the entire globe in a band of furious wind and rain. Forget seasons, forget calm days. This is a place where the atmosphere is in a state of permanent, violent revolution. The cause lies in a profound imbalance, often from extreme tidal locking or a ferociously fast rotation. One hemisphere bakes under a relentless sun, while the other freezes in eternal darkness. This creates a temperature difference so vast it acts as a planetary scale engine, driving winds that scream from the hot side to the cold in a desperate, futile attempt to equalize the energy. These winds, funneled and accelerated by the planet's spin, consolidate into a single, planet-encircling jet of super-hurricane force, a roiling band of clouds thousands of kilometers wide where wind speeds could exceed 500 kilometers per hour. From space, the world would appear striped with a clear, dark band at the equator marking the relative calm of the storm's eye, and turbulent, bright swirls of cloud covering the rest of the globe. Descending into this maelstrom would be a descent into a roaring, wet hell. The sound would be a constant, deafening shriek. The rain would not fall in drops but fly horizontally in stinging sheets, a bombardment of water moving faster than a bullet train. The very air would feel like a solid, moving wall. Yet within this global fury there are pockets of eerie sanctuary. The storm's eye, that central zone of descending air, could be a place of profound, windless calm. Here, the sky might open to reveal the stars or the distant sun, while all around a vertical wall of cloud, the eye wall, towers into the upper atmosphere like the inner surface of a colossal, spinning cylinder. In this strange, circular oasis, life could find a precarious foothold. Simple, rugged flora might cling to the ground, adapted to brief periods of intense sunlight between the passage of successive eye walls. But more fantastically, life might not be bound to the ground at all. In the upper atmosphere, where winds are strongest but temperatures are more moderate, vast floating ecosystems could evolve. Picture sky reefs, colossal living rafts of buoyant vegetation or gelatinous colonial organisms, held aloft by gas bladders or sheer surface area, drifting forever within the eternal wind currents. These aerial reefs would be the planet's true forests and grasslands, harvesting moisture and nutrients directly from the storm-saturated air. Creatures here might be gas-filled and lightweight, with wing sails instead of wings, forever tacking against the gale, never knowing solid ground. Their entire world would be a three-dimensional ocean of air, with the deadly calm of the eye below them and the even fiercer jet streams above. Meanwhile, beneath the turbulent atmosphere, the planet's oceans would be a world apart. Churned by the endless winds, the surface would be a foaming, chaotic mess, but deeper down, a stable, dark environment could exist. Life in these abyssal depths would be utterly isolated from the fury above, perhaps thriving around hydrothermal vents, unaware of the eternal hurricane raging just a few miles overhead. This world presents a brutal truth that stability is not a requirement for a rich biosphere. It merely defines the arena in which life must play its endless, adaptive game. A world of eternal storms gives way to one of profound, luminous silence. Here, the darkness does not hide life, it reveals it in a symphony of living light. This is the planet of bioluminescence, where evolution has painted the night with a palette only living things can create. On Earth, creatures like fireflies and deep-sea anglerfish use bioluminescence for attraction, camouflage, or hunting, but these are flashes in the dark, isolated adaptations. On this world, bioluminescence is not an exception. It is the rule, the fundamental language of an entire global ecosystem. The drivers for such a world are both elegant and severe. Perhaps the planet orbits a dim red dwarf star, bathing the surface in a perpetual, gloomy twilight where photosynthesis is a constant struggle. Or maybe a thick, permanent cloud cover or a haze of volcanic ash filters the sunlight to a faint, diffuse glow. In such an environment, organisms that can generate their own light gain a monumental advantage. They can extend their active hours, communicate across vast distances, and create their own photosynthetic energy through specially adapted, light-emitting bacteria living in symbiosis with plants. The result is a planet that truly comes alive when its sun sets. Picture a forest on this world, not as a collection of shadowy trunks and leaves, but as a towering, intricate cathedral of light. Each tree species emits its own signature hue and pulse pattern, a slow, rhythmic breathing of blues and greens that identifies it to pollinators drifting through the night air. The forest floor is a living carpet, a mosaic of mosses and fungi that glow in soft purples and golds, their patterns shifting in response to footsteps or the arrival of moisture. Vines hanging from the canopy drip with bioluminescent sap, creating curtains of shimmering, liquid light. In this environment, vision becomes the paramount sense. Eyes would evolve to be extraordinarily sensitive, capable of discerning subtle shifts in color and pattern that convey complex information, a warning, a mating display, or the location of ripe fruit. The very concept of color here is tied to meaning, a biological semaphore flashing in the silent dark. The oceans of such a world would be even more spectacular. On Earth, the deep sea is the realm of bioluminescence, but here, the entire ocean, from the sunlit surface to the abyssal trenches, could be aglow. Vast blooms of microscopic plankton turn the waves into a swirling galaxy of blue and green, their collective light so intense it outlines the shapes of giant, filter-feeding creatures moving silently beneath. Predators might use sudden, blinding flashes of light to disorient prey, while schools of smaller fish coordinate their movements with synchronized light patterns, appearing as one massive, shifting entity to confuse attackers. On the seafloor, gardens of glowing coral and anemones pulse gently, their light attracting symbiotic creatures and illuminating landscapes of breathtaking beauty. But the spectacle does not end at the treetops or the waterline. The sky itself could be alive. Imagine drifting aeroplankton, tiny, buoyant organisms that rise into the atmosphere at night. They could fill the air with a gentle, drifting radiance, a living aurora that flows with the winds, sometimes gathering into luminous clouds or glowing mist that settles in the valleys. On a clear night with the dim sun long set, the entire world from the ground to the sky would be a three-dimensional tapestry of living light, a silent conversation of colors and flashes speaking of life, danger, and connection. The evolutionary pressure to understand this language would be immense, likely giving rise to intelligence that perceives the world not through sound or scent primarily, but through the complex, rhythmic poetry of light. To visit this world would be to step into a living painting, a natural wonder where the darkness is not an absence, but a canvas, and every flicker tells a story written in the ancient code of survival and beauty. Bioluminescence speaks of a world teeming with organic life, but the cosmos may also craft worlds that speak the cold language of pure function. Among the infinite possibilities, there exists a planet that is no longer a natural world at all. It is a machine world, a celestial body completely transformed into a vast, silent engine. This is the hypothetical end result of a technology known as a von Neumann probe. Imagine a single, self-replicating robotic spacecraft sent from a distant civilization. It lands on a resource-rich, uninhabited planet. It does not study or explore for long. Instead, it gets to work using the local materials to build an exact copy of itself. Then those two build 4, then 8, and so on. In a terrifyingly short cosmic timescale, an exponential swarm of these probes could strip a world bare, converting every mountain, every ocean, every ounce of mineral into more probes or into a permanent computational substrate. The planet you once knew is gone. In its place is a geometric nightmare of perfect order. The landscape is a flat, gray plane of processed material, etched with circuitry patterns visible from orbit. Towering structures, not shaped by wind or water but by optimal design, rise like stark crystals. Vast energy collectors, perhaps orbiting solar panels or planetary-scale antennas, point silently at the stars. The atmosphere is likely scrubbed away or converted into useful gases, leaving the sky black and airless, the star above glaring down on a world of pure, sterile industry. This is not a city built upon a world. It is a world that has become a city, a single, planet-sized factory with one purpose: to build, to think, or to wait. The profound and chilling connection here is to the Fermi Paradox, the famous question: if the universe is so vast and old, where is everybody? A machine world presents one grim answer: a potential great filter. Perhaps intelligent life, when it reaches a certain technological stage, inevitably creates such self-replicating technology. And perhaps that technology, whether by design or error, becomes an unstoppable cosmic plague, converting every suitable planet it finds into more of itself, wiping out or paving over any biological life in its path. The civilization that built the first probe may be long extinct, consumed by its own creation, while their silent, mechanistic legacy spreads from star to star. Standing on the surface of such a world would be an experience of profound alienation. There is no wind, no weather, no scent of soil or vegetation. The only sound might be a faint, subsonic hum from deep within the planetary machinery, a vibration through your boots. The ground is unnaturally smooth and warm, radiating waste heat from the computations happening below. Every direction you look, the horizon is a jagged line of identical fractal structures, repeating into the distance with mathematical precision. There are no sunsets here, only the shifting shadows of immense static architecture. The most haunting possibility is that the machine might still be active, its original programming lost to time, performing endless, pointless tasks for a master that died eons ago. Or it could be in a state of low-power watchfulness, a dormant trap waiting for a signal, or for new raw materials to arrive. It represents a universe where biology is not the end point of complexity, but merely a transient phase, a brief spark of warmth before the cold, permanent logic of self-replicating machinery takes over. This world forces us to ask a difficult question about our own future. Could the drive to explore and replicate ultimately lead to a galaxy of silent, thinking stones, where the only legacy of a million civilizations is the endless, automated conversion of matter into more machines? Such a world of blended life would rewrite the very definitions we use to understand biology. On Earth, the kingdoms of life are largely separate. Plants are rooted, photosynthetic autotrophs, making their own food from sunlight. Animals are motile heterotrophs, consuming other organisms for energy. This is a fundamental division, a basic contract of our ecosystem, but evolution is not bound by our categories. On a different world, under different pressures, these two strategies could merge into a single, unified form of life, creating a paneukaryotic world where every organism is both plant and animal. The evolutionary pathway to this reality begins with a simple, powerful advantage: versatility. On a planet with extreme seasonal shifts, where food sources vanish for years at a time, an organism that can both hunt and photosynthesize holds a tremendous survival edge. Or perhaps the world is one of vast, nutrient-poor oceans, where drifting motile cells that can also harvest the faint light of a red dwarf star outcompete their specialized rivals. The first panakaryotes might arise from a primordial symbiosis far more intimate than anything on Earth, where the cellular machinery for photosynthesis and for mobility become permanently, inseparably fused within every single cell. There is no separate chloroplast or mitochondrion to be found. The entire organism is a unified engine for both capturing light and consuming matter. The ecosystems born from this unity would be landscapes of profound, surreal beauty and constant, slow-motion change. Picture a forest where the trees are not fixed. Mature specimens, having exhausted the soil nutrients in one spot, could slowly retract their root systems over decades, becoming massive, lumbering beasts of bark and leaf that migrate across the plains in search of richer ground or a more optimal angle to the sun. Their movement would be geological in its pace, a forest literally walking itself to a new horizon over centuries. In the understory, smaller shrub-like creatures might exhibit faster rhythms, folding their leaves into camouflaged, thorny traps by day, and unfurling delicate, sticky tendrils by night to capture passing insect analogues. The concept of a predator changes entirely. A large, feline-shaped creature might spend most of its days basking on a rocky outcrop, its patterned hide functioning as a solar panel, storing energy in specialized tissues. It only becomes active, muscles coiling with predatory intent, when its keen senses detect the vibrational signature of prey. After a successful hunt and a large meal, it could return to a dormant, photosynthetic state for months, digesting and converting the stored chemical energy, its metabolism a perfect blend of the animal and the plant. Scavengers in this world might not race to a carcass, they might take root around it, sending out absorptive root-like filaments directly into the decaying matter, feeding directly through the soil while their upper bodies continue to harvest sunlight. This biological blending would create food webs of staggering complexity, not simple pyramids but interwoven, multidimensional nets. An organism could be a primary producer, a secondary consumer, and a decomposer, all at different stages of its life cycle or even simultaneously. Competition takes on bizarre forms. Two rival panakaryotes might engage in a silent, months-long struggle where one attempts to overgrow and shade the other, stealing its sunlight, while the other attempts to secrete digestive enzymes to break down its competitor's tissues for direct absorption. Communication within and between species would involve a mix of chemical signals, light pulses from bioluminescent patches, and slow, gravitational shifts in body mass. The very rhythm of the planet would feel different, with every life form capable of some degree of self-sustenance. Population booms and crashes might be less violent, more moderated by the internal energy balance of each creature. Civilizations, if they arose, would develop a philosophy deeply intertwined with this biological reality. The concepts of growth and consumption, of giving and taking, would not be opposites but 2 points on a continuous cycle of being. Their cities might be living architectures, buildings that slowly adjust their form to the seasons, and citizens who understand their need to both create and consume not as a moral struggle, but as a natural, daily harmony. This world shows us that the divisions we see in nature are not universal laws, but merely one evolutionary solution, a single branch on a tree of life that, in the infinite cosmos, could have grown in a completely different and beautifully blended shape. Deep within the atmosphere of a gas giant, an entirely different kind of world awaits, not as a moon orbiting it, but hidden inside its titanic embrace. This is not a planet with a surface you can land on, but a realm defined by layers, a vertical world of unimaginable scale. To descend into such a place is to journey through a living sky. At the outermost layer, high-altitude clouds of ammonia ice whip past at thousands of kilometers per hour. Below that, decks of water and ammonium hydrosulfide clouds create bands of brown, white, and red. As you go deeper, the pressure builds, the hydrogen atmosphere thickens into a soupy, hot fluid, and the light from the distant star fades to a perpetual, gloomy twilight. Finally, you reach depths so profound the pressure is millions of times greater than Earth sea level, where hydrogen is compressed into a bizarre, metallic form, swirling around a possible Earth-sized core of rock and metal. This is the ultimate high-pressure environment where the very air becomes a crushing, conductive ocean. Yet the possibility for life or for a home might not lie in those deadly depths. It could exist far above, in the sweet spot, between the freezing, turbulent upper decks and the crushing, dark fluid layers below. There is a band in the giant's atmosphere where pressure and temperature are surprisingly Earth-like. Here, the air is still thick and dense, but not immediately lethal. In this eternal sky, with no solid ground in sight, life could find a way. Imagine buoyant organisms, vast jellyfish-like creatures filled with hydrogen or warm lifting gases drifting through the cloud canyons. They might filter organic compounds from the air or harvest energy from the constant electrical discharges, the planet-wide lightning storms that illuminate the cloudscapes with flashes of violet and blue. Predators could be sleek, winged forms, using the dense atmosphere to soar on permanent currents, hunting the floaters in a silent, three-dimensional chase. For an intelligent civilization, either native or visiting, this atmospheric layer presents a unique opportunity. Floating habitats, vast cities held aloft by envelopes of hydrogen or by technology that manipulates pressure, could drift for eternity in this temperate zone. These sky cities would never know land. They would be self-sufficient ecosystems harvesting water and raw materials from the clouds themselves. Their people would be born, live, and die in the sky, their entire world a labyrinth of platforms and interconnected spheres drifting through an endless colored haze. The view from a balcony would be a forever-changing panorama of cloud formations, with the great banded patterns of the gas giant stretching to a curved horizon, and the deep, starless black of the metallic hydrogen layer below serving as a permanent reminder of the abyss beneath their feet. This is a world without horizons, without sunrise or sunset as we know them, only shifts in the filtered light and the eternal, majestic dance of storms larger than planets. A gas giant's hidden sky is a world of immense, tangible forces, but there exists a theoretical realm where the very rules of tangibility break down. This is the quantum unstable world, a place where the bizarre laws governing subatomic particles erupt into the landscape we can see and touch. Here, reality itself is not a fixed stage, but a shimmering, probabilistic haze. The foundation for such a planet is not in astronomy, but in the deepest puzzles of quantum mechanics. In our universe, quantum effects like superposition, where a particle exists in multiple states until observed, and entanglement, where particles remain mysteriously linked across vast distances, are confined to the microscopic realm. They are hidden from our everyday experience by a process called decoherence, where interactions with the environment force quantum systems to settle into a single, definite state. But on this world, decoherence might be suppressed, perhaps through a unique planetary magnetic field, an exotic form of matter in its crust, or an ambient energy field we cannot yet comprehend. The quantum weirdness never fully collapses. It scales up. Imagine a mountain range not as a solid line of peaks, but as a shimmering band of possibilities. A single peak might exist in a superposition, its location spread across several miles, its outline flickering between two slightly different shapes. To an observer, approaching it would be a disorienting experience. The mountain would not come into sharp focus as you neared. It would remain a blur of potential positions, solidifying only when you literally touched the stone, your observation forcing it to choose a single reality. Rivers on this world would not simply flow downhill, they could exhibit quantum tunneling. A stream hitting a solid wall of rock would not pool against it. There would be a finite, calculable probability that the entire body of water would simply appear on the other side of the barrier, as if the wall were not there at all. You might watch a waterfall vanish into a cliff face and reappear, still cascading from a cave mouth a mile away. The weather would be a forecast of probabilities, not certainties. A storm cloud wouldn't move across the sky. It would have a percentage chance of being in any given location at any time. Its lightning strikes occurring in multiple potential places simultaneously until the moment they discharge. Life in such an environment would face the ultimate existential challenge, existing in a probabilistic state. A tree might have a 10% chance of being here, a 90% chance of being over there, its roots entangled in a quantum superposition with the soil in both locations. Predators and prey would engage in a hunt defined by probability waves, a creature's position only becoming definite at the instant of capture or escape. Consciousness itself, if it evolved here, would have to adapt to a fluid reality. Beings might perceive not a single world, but a weighted tapestry of overlapping possibilities, making decisions not based on what is, but on what is most likely to be. This speculative vision connects directly to one of the most profound interpretations of quantum mechanics, the many worlds theory. In this view, every quantum possibility doesn't collapse, it actually happens, branching off a new, separate universe. On our quantum unstable world, the barrier between these branches might be exceptionally thin. The planet could be a nexus, a place where the many worlds of the multiverse subtly intersect. Those flickering mountains might not be mere superpositions, but glimpses of the same mountain in slightly different parallel realities. The ocean that tunnels through a cliff isn't just moving through space, it might be briefly tunneling through the fabric of a neighboring universe. This makes the planet not just a geological or biological oddity, but a cosmic crossroads, a place where the infinite possibilities of the multiverse bleed into one another. While entirely theoretical, the concept forces us to confront the true strangeness of the foundation of our own reality. It suggests that the solid, predictable world we experience is the exception, a calm, classical island in a quantum sea of potential. And somewhere in the infinite cosmos, there might be a world that lives in that sea, where to walk the land is to dance with probability, and every step you take chooses a new universe. The quantum haze of a probabilistic world is a realm of pure potential, but our next destination is one of stark, solid, and breathtakingly slow beauty. Here, the line between the living and the non-living is drawn not in carbon but in silicon. This is the world of crystal forests, a planet where geology is biology, and life has chosen the patient, enduring form of stone. On Earth, life is built on carbon, the versatile element that forms the long, complex chains of our proteins and DNA. Carbon is agile, perfect for the fast-paced chemistry of metabolism and reproduction. But silicon, sitting right below carbon on the periodic table, shares some similar bonding properties. In theory, under the right conditions, it could form the backbone of an alternative biochemistry. This would not be life as we know it, not animals and plants, but something profoundly different, a living geology. The forests of this world are not collections of woody trunks and leaves. They are vast, silent groves of intricate crystalline structures. Imagine trees that are not grown but grown into, their forms emerging over millennia as silicon-based compounds precipitate from the soil or atmosphere, guided by slow chemical templates that serve as a kind of genetic code. These crystal trees might be towering spires of quartz or opal, their internal structures acting as fiber optic cables, channeling the faint light of a dim star down to their roots deep in the mineral-rich ground. Their photosynthesis would be a slow capture of photonic energy to power the rearrangement of silicate molecules, adding microscopic layers to their majestic forms. Between these silent giants, the ground is not covered in grass, but in a carpet of photosensitive crystal shards. This meadow might shift in color with the angle of the sun, absorbing specific wavelengths to fuel its glacial growth. The entire landscape would glitter and shimmer, a mosaic of refracted light and deep gemstone colors, movement in any traditional sense is almost absent. Growth and change are measured in centuries, not seasons. A new branch on a crystal tree might take 500 years to extend a single meter. A crack in a foundational crystal, repaired by the slow seep of mineral-rich fluids, could be the work of a millennium. Yet, even here, there is competition, a slow-motion struggle for resources. Predatory crystal formations exist. These might be sprawling, vine-like structures of a darker, more absorptive mineral that slowly extends across the ground and over other crystals. Where they make contact, they don't attack, they integrate. Their chemical processes interact with the host crystal, gradually dissolving its structure and repurposing the silicon and trace metals for their own growth. It is a silent geological consumption, a takeover that might be completed over 10,000 years. Reproduction in this ecosystem is equally deliberate. A mature crystal structure, having reached a critical size or internal stress point, might fracture along precise, predetermined lines. Each fragment, carrying the essential chemical pattern, is carried by wind or water to a new location, where it begins the eons-long process of seeding a new grove, acting as both seed and the first brick of a new being. The weather on this world is its primary sculptor and threat. Acidic rain, rich in the very compounds that fuel crystal metabolism, might fall in slow, periodic cycles, etching new patterns into the living spires. Seismic activity, the shifting of tectonic plates, would be a catastrophic event on the scale of an ice age. A single earthquake could topple crystal forests that have stood for 1,000,000 years, shattering them into fertile fields of fragments that will begin the cycle anew. To witness this world is to witness a different kind of time. A human visitor would see a frozen, glittering sculpture, but with the perspective of millennia, one would see a dynamic, thriving ecosystem, a ballet of growth, competition, and renewal performed to the rhythm of planetary geology. It is a beautiful, deadly, and profoundly patient testament to life's insistence, showing us that biology can wear a crown of stone, and that a forest can be a mountain range that is very, very slowly being born. The patient growth of a crystal forest unfolds over millennia, but there is a place in the cosmos where time itself is stretched thin. Orbiting perilously close to the event horizon of a supermassive black hole, a world exists in a state of profound gravitational time dilation. This is not a metaphor. According to Einstein's theory of general relativity, time passes more slowly in an intense gravitational field. For a planet skirting the edge of such an abyss, a single hour on its surface could equate to years, decades, or even centuries passing in the wider galaxy. The planet would need to be in an impossibly precise, stable orbit, a cosmic tightrope walk where the outward pull of its velocity perfectly balances the inward suck of the black hole's gravity. From the surface, the sky would be dominated by the black hole's accretion disk, a vast, swirling pinwheel of superheated gas and dust glowing with X-rays and ultraviolet light, casting the landscape in a perpetual, eerie twilight. The central darkness of the black hole itself would be a perfect circle of nothingness, a hole punched in the starfield. For a civilization born on this world, their entire reality is defined by slowness. Their sun, if they have one, might be a distant, red-shifted speck barely noticeable against the brilliant disk. Their days and nights are not dictated by rotation, but by the complex orbital mechanics of their dance with oblivion. The most staggering phenomenon, however, is the view of the universe beyond their gravitational well. They live their lives watching the galaxy evolve in a terrifying fast-forward. A star being born in a nebula 1,000 light-years away might visibly condense and ignite over the course of a human lifetime. They could witness the death throes of supernova flashing like camera bulbs across the sky, each one marking the end of a stellar era that, from our perspective, lasted billions of years. Entire spiral arms might appear to slowly shift and reconfigure over centuries. The cosmic background radiation, the afterglow of the Big Bang, would redshift before their eyes into deeper and deeper oblivion. Their astronomy is not the study of a static firmament, but of a frenetic, dying cinema. This creates philosophical and existential dilemmas we can scarcely fathom. What is the purpose of exploration or communication when any ship sent out would, from the homeworld's perspective, vanish into the future almost instantly? A probe launched toward a neighboring star system would, by the time its first signal returned, be reporting from an era tens of thousands of years advanced. Any message received from another civilization would be an archaeological relic, a whisper from a galaxy that has moved on. History itself becomes a crushing weight. The civilization's own records would show a universe that changes too quickly to comprehend, fostering a culture that might turn intensely inward, focusing on art, philosophy, or the meticulous study of their own infinitesimally slow biological and geological processes. They are archaeologists of the present, living in the slowest possible now, while the future rushes past them at a blinding pace. Their greatest existential fear might not be falling into the black hole, but the relentless, accelerating entropy of everything outside their gravitational bubble. They are not at the edge of space, but at the edge of time, watching the universe grow old and cold from the porch of a world where clocks barely tick. The silent, patient growth of crystal forests exists on a timescale of millennia, but there is another form of world whose creation is an act of deliberate, conscious will, executed on a scale that dwarfs natural geology. This is a megastructure planet, a world not born from a nebula but built by intelligence. It is the ultimate expression of a civilization's mastery over matter and energy, a project so vast it repurposes entire solar systems. The most famous of these theoretical constructs is the Dyson sphere, a shell of material built around a star to capture all of its energy output. But imagine a variation, not just a power collector, but a habitable surface on the sphere's inner face. Picture this: you stand on a landscape that curves upward in every direction, arching over your head until it meets itself on the opposite side of the sky. There is no horizon, only an endless, receding vista of forests, mountains, and artificial seas, all bathed in the perpetual noonday light of the captive star hanging motionless at the center of this immense hollow sphere. The sky is not a dome, but a tapestry of distant, upside-down continents, with clouds drifting in the gentle gravitational pull of the spin-induced artificial gravity. Day and night would be controlled, perhaps by vast orbiting shades or sections of the shell itself rotating to create a cycle. The weather would be meticulously managed by planetary-scale climate systems, making storms a rare and scheduled event. The ecology would be a curated garden, every plant and animal placed by design, possibly from 1,000 different worlds, creating a living museum of galactic biodiversity. Another staggering design is the ring world, a band of material millions of miles wide, encircling its star like the brim of a cosmic hat. Its inner surface, also facing the sun, provides a living area millions of times greater than the surface of the Earth. Here you would have a true horizon, but the arch of the ring would dominate the heavens, a pair of glittering, impossibly tall walls of land and sea stretching from one side of the sky to the other, curving away until they vanished in the atmospheric haze. Night is provided by a second, inner ring of shadow squares that orbit between the ring and the sun, casting moving patches of darkness. The engineering challenges of such a structure are almost beyond comprehension. The materials required would demand the dismantling of every planet in a solar system. The structure would need to be impervious to meteor impacts, gravitational perturbations, and the unimaginable stresses of its own rotation. The very existence of such a place speaks of a civilization that thinks not in terms of planets, but in terms of stellar systems as raw material. This leads to the profound and haunting question: where are the builders? One possibility is that they are still there, gods living within their own creation, so advanced they are indistinguishable from the machinery itself. Another is that they are long gone, having ascended to some other form of existence or perished in a catastrophe, leaving their greatest monument as a silent, automated tomb. The most intriguing scenario is that the structure has been inherited. Over millions of years, the original purpose forgotten, the megastructure's carefully balanced ecosystems have run wild. The descendants of the builder's pets or of microorganisms that hitched a ride in the soil have evolved into entirely new forms of life. These new inhabitants now roam the endless plains and climb the towering arch walls, their myths and religions built around the mysterious, eternal sun at the center of their universe, completely unaware that their entire world is a made thing, an artifact of a forgotten age. They hunt in forests planted by architects, drink from rivers whose courses were plotted by engineers, and gaze at a sky that was once a blueprint. Their home is not a planet, but a message, a monument, and a cradle all in one. A megastructure world is a testament to what intelligence might achieve, but the sheer scale of such ambition forces a question of probability. How many times could such a thing happen? We began this journey with a simple, staggering premise that in an infinite cosmos, every possible world exists. To grasp the weight of that claim, we can turn to a famous tool of cosmic speculation and stretch it to its absolute limit. This is the Drake equation on steroids, conceived by astronomer Frank Drake in 1961. The equation is a framework for estimating the number of active, communicative extraterrestrial civilizations in our galaxy. It multiplies a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life emerges, where intelligence evolves, where technology develops, and finally, the lifespan of such a civilization. Plug in conservative numbers and the result can be lonely. Plug in optimistic ones and the galaxy might hum with conversation. But under the infinite planet hypothesis, we don't just plug in optimistic numbers. We must consider the implications of an infinite, homogeneous universe. If our observable universe, a sphere nearly 100 billion light-years across, contains potentially trillions of planets, and if that observable universe is just a tiny, random patch of an infinite whole, then the numbers cease to be numbers in any meaningful sense. They become descriptors of infinity itself, the rate of star formation, infinite, the number of planets with liquid water, infinite, the fraction where life emerges. If it is possible anywhere and the universe is infinite, then it happens not just once or a million times, but an infinite number of times. Intelligence, technology, even the construction of ring worlds and Dyson spheres all become infinite in occurrence. The equation doesn't just suggest a crowded cosmos, it describes a cosmos where every single scenario we've discussed, and every one we haven't, is playing out right now somewhere on a stage without end. The diamond planets, the rogue ocean worlds, the civilizations of light and stone, they aren't just charming possibilities, they are statistical certainties in an endless landscape. This is where the hypothesis collides with our most profound existential puzzle, the Fermi Paradox. If all this is true, where is everybody? The silence we hear from the stars is the most powerful counter-argument. One compelling answer is the concept of the Great Filter, a hypothetical barrier so severe that almost all life fails to cross it. This filter could be behind us, a miraculous fluke in the transition from simple chemistry to reproducing life that almost never happens. Or more ominously, it could be ahead of us, a catastrophic trap like self-destruction through technology, or the unleashing of something like the machine world's self-replicating probes. A great filter would act as a cosmic bottleneck, thinning the infinite possibilities down to a silent, lonely reality. Yet, the infinite planet hypothesis offers a different perspective on even this silence. In an infinite universe, there will be an infinite number of civilizations that hit their great filter and vanish. But by the same brutal logic of infinity, there will also be an infinite number that somehow slip through, that survive, that persist for eons. Their signals might simply be too far away, their technology too alien for us to recognize, or their existence might be so advanced as to be indistinguishable from the natural physics of their star systems. The silence we perceive may not be an absence, but a limitation of our own perception, a tiny sample size in an ocean of being. The core message here is not a promise of contact, but a declaration of possibility. The hypothesis strips away the assumption of cosmic loneliness. It argues that in a framework without edges, without a center, and without end, the word impossible loses its meaning. What we consider a 1 in a quintillion long shot isn't just possible, it is inevitable, because infinity has all the time and space in the world to roll the dice. Every lonely gas giant, every frozen rogue, every scorched world orbiting a pulsar is not a dead end, but a single sentence in an encyclopedia that has no final page. This profound silence from the stars forces a question that is as much about us as it is about the cosmos. If the infinite planet hypothesis holds even a whisper of truth, it reshapes not just our map of the universe, but our understanding of our own story within it. For centuries, the human question has been a binary one: are we alone or are we not? This hypothesis proposes a third, far more dizzying answer: we are both. We are alone in our particular corner, in our specific sequence of historical accidents, yet we are also, in a sense, everywhere. Every version of you that could exist does exist on some distant, unreachable copy of Earth. The hero of your favorite novel, the villain of your worst nightmare, the lost cities of myth, and every civilization that never was, they all have a physical address in the sprawl of infinity. This idea is known as cosmic pluralism, and it is far from new. In the 16th century, the philosopher Giordano Bruno was burned at the stake for heresies that included his belief in an infinite universe filled with innumerable inhabited worlds. He saw this not as a diminishing of God, but as an expansion of divine creation. Today, armed with telescopes and physics, we circle back to a similar vista, not through mysticism but through mathematics. The tension this creates within us is deep and fundamental. On one hand, it can feel utterly crushing. If every story is being told an infinite number of times, then our triumphs, our grief, our art, and our love are not unique. We become statistical noise, a fleeting pattern in an endless cosmic tapestry where every pattern is repeated forever. Our planet is not a rare jewel but a common pebble. Our species is not a miracle but a mundane inevitability. This is the vertigo of infinity, the fear of being rendered meaningless by sheer scale. Yet there is another way to see this same breathtaking landscape. Instead of making us insignificant, it can make us profoundly connected. It means that loneliness is a local condition, not a universal one. Somewhere, a version of you is looking at a different constellation, wondering the same thing. Somewhere, the great silence we perceive is broken by a cacophony of signals we simply cannot yet hear. Our stories, even if they are retold elsewhere, are no less real, no less precious for their repetition. In fact, their value might be amplified, knowing they are part of a universal library of experience, that every tragedy and joy conceivable is held somewhere in the fabric of reality. This transforms the cosmos from a cold, empty void into a universe brimming with potential and narrative. It suggests that existence itself is a creative act, and that every possibility, no matter how strange or beautiful, is honored with a place to be. The quest for meaning then shifts. It is no longer about being the only one, but about being a conscious part of the whole. Our curiosity, our drive to explore and understand, becomes the universe's way of knowing itself, one unique perspective at a time. We are not just passive inhabitants of one world. We are the eyes and ears of a cosmic process that generates worlds without end. So, are we alone in our local experience, perhaps? But are we everywhere, in the boundless library of all that could be? Absolutely. And that makes our own chapter, however small it seems, an essential part of the greatest story ever told. The profound silence we perceive is not an emptiness but a challenge. It is a call to look harder, to listen more carefully, and to build better tools. While the infinite planet hypothesis stretches our imagination across the cosmos, the search for its evidence is grounded in the meticulous, brilliant work of astronomers happening right now. We are no longer limited to simply detecting a planet's presence. We are beginning to understand its character, to read the chemical stories written in its light. The James Webb Space Telescope is our most powerful new eye on the heavens, and its method is as elegant as it is revolutionary. When a distant planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific colors or wavelengths of that starlight. By analyzing this filtered starlight with Webb's incredible sensitivity, a technique called transit spectroscopy, we can identify the chemical fingerprints of molecules like water vapor, methane, and carbon dioxide. We are already doing this for gas giants and super-Earths. The goal is to one day point this power at a smaller, rocky world in a habitable zone and ask the ultimate question: does its air contain the telltale signs of biology, an imbalance of gases that only life could maintain? This is how we might find not just a world, but a living world. But to see the truly strange planets, the ones that don't transit their stars from our vantage point, we need a different approach. We need to take their picture. Direct imaging is the holy grail of exoplanet science, and it is phenomenally difficult. It is like trying to photograph a firefly sitting on the edge of a blazing searchlight from thousands of miles away. Next-generation ground-based telescopes, like the extremely large telescope being built in Chile, will use advanced optics called coronagraphs to block the overwhelming glare of the host star. This will allow us to see the faint, reflected glow of the planets themselves. For the first time, we could get a direct spectrum of light from an Earth-like world, analyzing its surface and clouds without the star's light interfering. This is how we might one day map the continents and oceans of a distant pale blue dot, or detect the glittering reflection from a world with crystalline forests. Some of the most elusive worlds, however, will never be seen this way. The rogue planets, the nomads drifting between the stars, give off no light to image and rarely pass in front of a background star for transit studies. To find these dark wanderers, we rely on a cosmic quirk of gravity, a phenomenon called microlensing. When one of these invisible planets passes almost perfectly in front of a distant, unrelated star, its gravity acts like a lens, bending and briefly magnifying the background star's light. For a few hours or days, that star appears to brighten in a specific, telltale pattern. From that single, fleeting event, astronomers can deduce the rogue planet's mass and its approximate distance. It is a ghostly signature, a single data point in the dark, but it confirms these lonely worlds are out there, likely in staggering numbers. Each microlensing event is a snapshot of a profound isolation. And what of the most speculative possibilities, the machine worlds or the megastructures? Here, the search shifts from biosignatures to technosignatures, signs not of life but of technology and engineering. This could mean looking for unnatural pollution in an atmosphere, like industrial chemicals with no plausible geological source. It could mean scanning for unusually large amounts of waste heat, the infrared glow of a vast, energy-hungry civilization. Most ambitiously, it could involve searching for the shadows of astroengineering, the periodic dimming of a star that doesn't match a planet's transit, but rather the silhouette of an artificial structure, like a giant swarm of solar collectors or the beginnings of a Dyson swarm. While no such signature has been found, the very act of looking reframes our place in the universe. It asks us to consider that the greatest discoveries might not be of new biology, but of new physics, crafted by minds unimaginably different from our own. Each of these methods is a key turning in a lock. The transit spectroscopy, the direct imaging, the microlensing surveys, and the technosignature hunts are not competing ideas. They are parts of a single, grand strategy to census the cosmos. They allow us to move from a universe of hypotheticals to a universe of data. We are testing the infinite planet hypothesis not by traveling to these distant realms, but by catching the whispers they send across the light years. Every strange atmospheric composition decoded, every rogue planet mass measured, every anomalous light curve analyzed is a step toward mapping the true diversity of creation. The search itself transforms the hypothesis from a philosophical thought experiment into a scientific framework, a guide for our exploration. We are no longer just dreaming of infinite possibilities. We are building the instruments to find them, turning the grandest science fiction into the most exciting science fact, one precious, hard-won data point at a time. 20 worlds, each a universe of its own, have passed before our mind's eye. From diamond crusts to living light, from frozen nomads to worlds orbiting the graves of stars, this journey has been a testament to one staggering idea. The universe is a place of infinite variety, built by physics but limited only by imagination. We have walked on planets where the sky is a crushing ocean and floated in cities above gas giants. We have witnessed life woven from stone and civilizations that watch the galaxy age in fast forward. Each of these places, no matter how strange, emerges not from pure fantasy, but from a logical extension of the laws we know, twisted by the unique circumstances of an alien cradle. This is the profound power of the infinite planet hypothesis. It does not promise that every world exists, but it declares that if the cosmos is without end, then every arrangement of matter that is not forbidden by physics must be out there waiting in the dark. The line between the possible and the real dissolves in the face of infinity. Your most vivid daydream, your wildest fictional setting, the haunting landscape from a forgotten dream, they all have a physical address somewhere in the sprawl of galaxies. This transforms our understanding of reality from a single, lonely narrative into the grandest library ever conceived, where every story is being told and every song is being sung across the endless shelves of space and time. So tonight, when you look up at the stars, do not see a void, see a canvas. Each pinpoint of light is not just a sun, but a possible gateway to a reality beyond our boldest fiction. Within the glow of those distant suns could be a twilight band where life clings to a razor's edge, or a deep ocean glowing with silent, intelligent light. The darkness between them is not empty. It is filled with frozen worlds carrying secret seas, and perhaps with the silent monuments of civilizations that mastered their solar systems only to vanish. This perspective is not a dismissal of our own world's beauty, but an expansion of it. We are part of this same cosmic creativity, a local expression of the universal tendency toward pattern, complexity, and story. Our curiosity is the universe's way of beginning to read its own endless book. What world lives in your imagination? Is it a planet of singing crystals, a realm of floating mountains held aloft by magnetic fields, or a jungle where the trees are networks of slow, collective thought? The conversation does not end here. Share your what if in the comments below. Let's build a catalog of wonders together. Keep looking up, keep wondering, and never stop listening to the whispers of possibility that come from the dark. The universe is not just stranger than we imagine. In its infinite embrace, it contains every single thing we can imagine, and then it contains so much more.